this lesson, we're going to learn how to find global maximums and minimums. Sometimes we call these absolute maximums and minimums. First, let's define what they are. We're told that f has a global maximum if f of p, which would be the y value, is greater than or equal to all the other values. And we have a global minimum if f of p is less than or equal to all of the values. So let's just consider the graph that we see right here. And if we look here, we can see down here we have a global minimum because that is the lowest value on the entire graph. Now the way this entire graph is drawn, we have no global maximum because as it's drawn right now, it goes up forever on both ends, which means we don't have a particular one value that's bigger than all the others. But if we were to change these endpoints, and let's say we had one of them stopping here, and this one, say, stopping down here, then we might call this the global maximum. But if we have the graph we had before, where they went up forever, we would not have a global maximum. A global one is different than these ones right here. This right here, of course, is a local max. And this right here is a local min, because near those, so if we just take a look in the neighborhood near there, that's the highest point. And if I look over here in the neighborhood near this one, this is the lowest point. All right, so we have a new theorem here called the extreme value theorem. And an extreme value theorem says that if a function is continuous on a closed interval, then the global maximum and minimum will always occur and will be found at a critical point or an endpoint. All right, we're going to be applying that, so you're going to see that again. And let's go here and understand the difference between local and global. So let's pull this out. A local extrema will occur at critical points, and a function can have several local extrema, like the problems we've done where we have multiple local maximums or multiple local minimums. When we talk about a global extrema, it will occur at critical points or endpoints, and there's only one global max and one global min. So let's take a look at a few more graphs here. Here it asks us to identify the local and global extrema in the interval from A to B. Now when we look at this one is not defined here, so this is not on a closed interval. So we are not guaranteed to have both. We do happen to have a global minimum, but we do not have a global maximum, and we're not guaranteed one because it doesn't go all the way from A to B. Now let's look at this next graph. Here, if we go from A here, oops, I'll try and get that lined up. We go from A there to B over here. We're going to consider some y values. We're going to consider the y value at A. We're going to consider the y value at B. And we're also going to consider this critical value right here at this minimum. And we're going to look at those, and we are guaranteed, because we're on a closed interval, that we have a global max and a global min. And you'll notice this is the lowest point, so this is a global min. And this right here on the end point is higher than either of those two. This is the global maximum. Okay? And where those answers are depend on where our A and B are. So I'm just going to go back and kind of move A and B and show you how it could be different if we had A and B in different locations. So let's say I moved A over here, and let's actually even have B over here. If we did that, then our A, the y value here is there, and B is right here. And this time we have no critical numbers in there, and so there's our global max, and here's our global minimum. Now, what if we moved, oops, there we go. What if we moved B over here? And let's even move A over here to this endpoint. Then we're going to consider this point, an endpoint. We're going to consider Let's move B somewhere a little more interesting. Let's have it be right here. Let's say B is this point, and we have two critical numbers. We have to consider this one and that one. And then if A and B go from there to there, then we can see our highest point right there. That's our global max. And our lowest point is right there. That's our global min. All right, so as we see the different examples, we can see they always occur at a critical point or an endpoint. This time it was both critical points, one time it was just endpoints, sometimes it's a combination of the two. So let's try that with a problem, and we're going to just go through the steps that are going to happen when we find global max or min. So we're going to figure out what the values are at the endpoints. We're going to find the critical numbers. We're going to evaluate the value function at the critical numbers. And then we'll pick the biggest y value for the maximum and the smallest for the minimum. All right, so let's try a problem like you'll see in your homework. So here's our first one. And we're given g of x equals 4x minus x squared minus 5. And I like to find my critical numbers first. So we're going to do that first. G prime of x equals 4 minus 2x. I'll set that equal to 0. And I can see that my critical number is going to be when x equals 2. All right. The next thing I'm going to do is make a chart of values. So I'm going to have x and g of x. And remember that our theorem said that the answer is either at an endpoint, there it is, 0 and 3, or at my critical number 2. I'm just going to list them in order. So my smallest x was 0. That's an endpoint, and I'm just going to label that so I know where that came from. The next one, 2, is a critical number. And then my next number, 3, is another endpoint. And now I'm going to plug those into my function right up here. That's why I labeled this as g of x, to see what the different y values are. So I plug 0 in here, 0 minus 5, that's negative 5. See this one, I'm going to put in a 2, so 8 minus 4 minus 5, so it looks like 8 minus 9, or negative 1. And then for this last one, when I plug it in, let's see, plug in, I get 12 minus 9 minus 5, so it's like 12 minus 14 is negative 2. And I look at those values and I say, okay, which one's the biggest? And there it is. Negative 1 is my max. And which one is my smallest? That'd be negative 5 is my minimum. And there we go. I have found the global extrema. Now I want to point out the difference between two questions. So I'm going to phrase two questions here. If I asked you, where is the global minimum? And they'll use this different language, especially when you get to multiple choice questions on the AP exam. So if they asked you, where is the global minimum, you would say, at x equals 0. But if they were to ask you, what is the global minimum, you would answer the y value. And you would say the global minimum is negative 5. Okay, so the difference between where and what. X tells you where it occurs, y tells you what it is. All right, let's try another problem. So this time we're asked to do the same thing, but our function is y equals x cubed e to the negative x. So I'm going to start by taking the derivative. Y prime equals x cubed left alone. Derivative of e to the negative x is e to the negative x times negative 1. I'm going to put that out here. Plus derivative of x cubed is 3x squared e to the negative x left alone. So let's see, I'm going to set that equal to 0, and I'm going to factor out what they have in common. So I see they both have at least an x squared, and they both have an e to the negative x. And so then when I factor that out, this first term is left with a negative x, and my second term is left with a 3. And I can see that my critical numbers from here is 0. I remember that e to the negative x is always positive. And then here I'm going to get a critical number of 3. Okay, so I'm going to make a table like I did before. So here we go. My endpoint, my first one is 0. It's also a critical number, so either way it becomes an important point. My next one is my critical point, 3. And my next one is going to be 5, which is my other endpoint. These are my x values, and I want to know what are my y values. And this time I'm going to pull up my calculator to help me out. So let's put that function into the calculator. So y equals, let's clear that out. So I need x to the third times second e to the negative x. And I'm going to go ahead and use my table function. So I'm going to go to table set and change it to ask. So I can ask for the 3 values I want. Second quit, second table. All right, so here we go. Let's put this over here. And I want 0, and I want 3, and I want 5. And just because I can, I'm going to drag that over here. Okay, so there are my values. I'm just going to copy them over onto my table here. So 0 is 0, 3 gives me 1.3443, and 5 gives me 0.84224. There we go. And now I can see that my maximum is the biggest of those. That looks like this one right here. And my minimum is the smallest, which is this first one right here. And again, if I asked you where is the minimum, you would say 0. If I asked you what is the minimum, you'd still say 0. But if I asked you where is the maximum, you would say it's when x is 3. If I asked you what is the maximum, you would tell me 1.3443. All right, one more problem. This problem looks like it's worded differently because it says find the best possible bounds for the function on the given interval. But it's actually the same problem. So this interval here, we can think of it in calculator world as being x minimum and x maximum. And when it asks for the best possible bounds, what it's really asking for is what is the y minimum and y maximum. In other words, if I graph this on my calculator, I want my function to go as high as the top and as low as the bottom. I would have that perfect window that showed everything. That is not the graph of this function. All right, so all we're really finding is the absolute minimum, that would be my y-min, and the absolute maximum, that would be my global maximum. All right, so here we go. Start the same way as before. We're going to find the derivative. F prime equals derivative of x is 1. Derivative of natural log x is 1 over x. We'll set that equal to 0. Let's see. 1 over x equals 1, and x equals 1. All right, so we have our table of values we're going to need to do. We have x and f of x, and we're going to plug in 0.1 because that's our first endpoint. Then we're going to plug in 1 because that's our critical number. By the way, all of these problems have one critical number, but you could have more than one. And we're going to plug in x max, which is our other endpoint. All right, let's see. I'm not knowing natural log of 0.1, so I think this is another good problem to go ahead and put it into our y equals. So we have x, let's better look at it again, x minus natural log x minus natural log x. And let's go to our table. And this time we need 0.1. Notice that's why it's not 0. It gives us an error. So 0.1, 1, and 5. So let's see. Let's drag that down again. So we've got 2.4026, 1, and 3.3906. 3.3906. Okay, so we can see that as we look at this, there's my minimum and there's my maximum. So when we are asked for the best possible bounds, we're basically saying that our y values are going to go from 1 to 3 point, and I'm going to just round it to 3.4 for our purposes, okay? So let's just see how that looks on the calculator if I'm to graph this. So we already have it in y equals, so that's good. If I go to my window, I can make my x go from 0.1 to 5. And I'm going to go to my y, and I'm going to use these from 1 to 3.4. And when we hit graph, you're going to see there's my graph. Bring that over here. And you can see that my lowest point is at the bottom of the graph, and my highest point, if I move away from that, there we go, my highest point is at the top of the graph. And there's that whole window. I go from all the way from the left to the right, and all the way from the top to the bottom. And you can see our minimum happened at a critical value, and our maximum this time happened at an endpoint. All right, that should be enough for you to be able to do assignment number 3.